Alrighty, year 12, where are we? Whoa, we're up to 9L already. Wow, time flies when you're having fun, doesn't it? Limits and continuity. Cool. You guys have looked at limits before in year 11, so there should be no surprises here. When we talk about some of these things, this is a bit of a refresher, but you can read there how the notation works. Limit as x approaches a of f of x equals p. It says that the limit of f of x as x approaches a is p. Cool. We can also say that as x approaches a, f of x approaches p. Cool. So that's pretty cool there. You can be asked to actually calculate some of these limits. Yeah. So it says find the limit as x approaches 2 for 3x squared. In this particular case, it's a matter of substituting 2 in here. We get that it is equal to 12. Essentially that's saying as x gets closer to 2, the value of 3x squared gets closer and closer to 12. Cool. You can get these situations here where we've got a function except when x does not equal 2, or except when x equals 2. It says find the limit of x as x approaches 2 for that particular function. Obviously that's in there because if that was 2 they'd be dividing by 0 and that'd cause problems, so that's why that's there. In this particular case what happens is we need to factorize the top line here, and then we can do some simplifying. So that x take away 2 cancels out that x take away 2. That fits into itself once, that fits into itself once there. Just leaves you with 2x take away 1. Yep. Now, once you've simplified it down, you can substitute in the 2 to find the limit of that. Substituting 2 in, 2 times 2 is 4, take away 1, it's equal to 3. Yep, so you can write that out. Yep. Cool. Now, essentially, again, this is if you had to sketch it, obviously it's the equation 2x take away 1, which is a straight line, except when x is equal to 2, so at x equals 2, there's a gap. Yep, it's not included in that. Yep, so you would sketch it as such. There are some rules that we need to follow regarding limits. Have you for you to read those there. But essentially, if you've got the sum of limits, it's just you add them together. Multiplying them, you multiply them. Product is the product of the limits, and the quotient is the quotient of the limits. Cool. So let's see this in action here. It says limit as h approaches 0 for this one here. Alright, to work that out, we need to work out the limit as h approaches 0 of 3h, which we can do, which is 0. 3 times 0 is 0. And then also work out the limit as h approaches 0 for 4. In this case, it's 4. Add those together. It's the sum of both of those, sorry, which is 4. Here, we're multiplying 4x and x plus 2, so we need to work out the limit of each of those and do the multiplication here. So limit as x approaches 2 for 4x is 8, and the limit as x approaches 2 of x plus 2, 2 plus 2 is 4. We do the multiplication of those limits, we get 32. Pretty happy with these. Division here, same difference. Top line of the quotient, bottom line of the quotient. Work out the limits. 17 divided by 1 is 17. Cool. We are powering through these. Example 42. Oh, these ones here, before you can go ahead and work through these, we do need to factorize. Yep. So here we've got x squared take away 3x. X is common to both those. It can be taken as a common factor. You're left with x take away 3. Good news is they cancel out, and you're left with just x. So essentially you need to evaluate limit as x approaches 3 of x. It's going to be 3. Yep. Here we need to factorize the top line. It factorizes to x take away 2, x plus 1. Happy days, they cancel out, and we're left with the limit as x approaches 2 of x plus 1. Substituting 2 into there, it's going to be 3. Cool. This one here, oh cool, factorizing both the top and bottom line, we get these. There's some cancelling out that can be done. Now we need to work out the limit of the top line of the quotient, the limit of the bottom line of the quotient. It's 1 over 8. Cool. In the past as well, you would have seen left and right hand limits. So you do need to know your right and left hands. Actually, is this mirrored image? I'm not sure. I'm just moving my hands around, but imagine you've got your hands in front of you. Where it's approaching from the right-hand side, the limit, they use this notation with a little positive. Yep, so it's coming from the right-hand side, it's a positive. Where it's coming from the left-hand side, so over here from the left-hand side, they use a little negative here, x as approaches from the left-hand side. It says the limit as x approaches a exists only if both the limit from the left and the limit from the right exist and are equal. Yep. So if they're the same on both sides, then the limit at that particular point exists. Cool. Now, this comes into play where you have what they call piecewise defined functions. Last year I referred to these as hybrid functions, but they're using this word now. So hybrid functions, piecewise defined functions, where there are separate parts to the function. Limit might not be able to be calculated at each part. Yep. So you can see here on some occasions on the left hand side it's not the same limit as it is over on the right hand side. So the limit over here is not the same as the limit over on this side here. So there are some occasions where it cannot be defined. Likewise, same with the rectangular hyperbola. Obviously, limits over this side is not going to be the limit as the same as over here. There's a gap. You can read all this as well. So there are some occasions where the limit cannot be calculated. Essentially, they can ask you about continuity at a point. And it says a function with the rule f of x is said to be continuous at x equals a if the graph of y equals f of x can be drawn through the point with coordinates a f of a without a break. Otherwise, there is said to be a discontinuity at x equals a. Cool. Also, it talks about function of f being continuous at the point x equals a if the following conditions are met, which they've listed there. It says a function is discontinuous at a point if it is not continuous at that point. Okay, so essentially the way I go about doing these is if you can draw a function without taking your pen off the page, obviously it's continuous. Yep. If you are going to draw it and you had to take your pen off the page to draw it, it's going to be discontinuous at that point. So here, consider I'm drawing this here, I'm sketching it. In order for me to be able to sketch this and put that dot there and then continue sketching, and there's a gap there with that little open circle, I had to take my pen off the page at that particular point. So you would say at that particular point it is discontinuous at x equals 1. Yep. Likewise here, I can sketch, I have to take my pen off the page at x equals -1 to be able to continue drawing. So it's discontinuous at that particular point. Likewise here, I'm continuing drawing, I take my pen off the page at 1 to go up to this section here. Yep, so it's also continuous, discontinuous at that particular point at 1. Yep, and it talks about y in terms of limits on either side, or you can use the fact that you'd have to take your pen off the page. Likewise here, this one, I'd have to take my pen off the page at x equals 1 to be able to draw that. So it's discontinuous at that particular point. If you're talking about limits, the limit at this particular point from the left-hand side, so coming from the left-hand side here, is equal to 1, or about 1. Whereas if you're coming from the right-hand side, as it approaches 1 here, it's equal to 2. They are not the same on both sides, so it's not continuous at that point. That's the way to define it by limits. Yep. Alrighty. There are some summary notes that are listed there. Happy for you to have a read through the last example yourself and make some notes based on the summary here. Good luck with limits and continuity. Bye for now.